Hey everybody, I'm Nick Suarez. I'm a research assistant for Peter Willis and Dr. Shenoy. This presentation is on the mesh tree protocol and how we are modifying the protocol to be implemented in data center networks. In this presentation, I'll first go over the basics of mesh tree protocol and an overview on data center network fundamentals as an introduction. Then I'll go into MTP for data center networks. Okay, so first we'll go over MTP. So what is the purpose of MTP? Due to a growing demand for switch networks and limitations of current loop avoidance protocols, MTP and the mesh tree algorithm provides a clean slate solution. Switch networks with organizations, service provider and backbone provider networks, and data center networks all have a growing demand. Switch networks use mesh topologies to provide physical redundancy. To carry broadcast, multicast, and unicast traffic without looping, switch networks use loop avoidance protocols. Spanning tree-based protocols and Dijkstra tree-based protocols are currently being used in networks to achieve this. Spanning tree and rapid spanning tree both have high convergence latency and root switch failures, and Dijkstra tree-based protocols have high computational overhead, also causing poor network performance. To handle these challenges, the clean slate solution of a mesh tree protocol was introduced. The mesh tree protocol uses multiple pre-constructed non-looping paths. This way, when there's a link or a device failure, the topology can converge almost immediately to a different pre-constructed tree that doesn't need that link. The protocol also includes decoupled broadcast and unicast frame forwarding paths to improve link utilization, as well as faster failure detection and dissemination. This leaves the network with minimal downtime and isolated failure impacts. Okay, so now that we talked about the basics of MTP, I'll give some background on data center networks before I talk about MTP for data center networks. So, as written here, a data center is a facility composed of networked computers and storage that businesses or other organizations use to organize, process, store, and disseminate large amounts of data. Data centers have massive scale, and modern data centers can have from a few hundred to 100,000 servers in a single location. The networks also need to be resilient and have a constrained blast radius in case of failure. With an increase in server-to-server communication and high connectivity requirements, a rethink to how these networks operate is required. Data center networks are designed to use simple switches and build redundancy straight into the topology. Clos and fat tree topologies are more suitable for DCNs than a traditional network because of cost, complex software, and very poor convergence rates causing catastrophic failures. As mentioned before, data centers are a pool of resources, and the DCNs interconnect all of the data center resources together. DCNs are more scalable and can connect tens to hundreds of thousands of servers. The DCN must use a topology that can provide redundancy, fast communications, and load balancing. Here's a list of some of the various data center network topologies that are commonly found in data centers. We will be focusing on the tree-based DCN topologies here in this presentation. Some challenges that arise with DCNs are scalability and high cross-sectional bandwidth. Scalability can be a challenge due to the large number of nodes that are going to be using the network. The number of nodes can be as high as hundreds of thousands. Cross-sectional bandwidth is defined as the bidirectional data rate that can pass between two parts of the network if it's divided into two equal halves. Here's an example of a folded Clos topology. The green rectangles are network switches, and the gray boxes are server racks. The switches on the top of the server racks are commonly called top-of-rack switches, or TOR devices. Here, the TOR devices are in the leaf of the folded Clos topology. If one server wants to talk to another server rack, we'll always have to go 3 hops away. One hop to the TOR switch, another hop to the spine switch, and another hop to the destination TOR switch. This topology provides rich connectivity due to the large number of connections between spine and leaf devices. Okay, so now we can talk about MTP for data center networks. So here's the same folded Clos topology that we saw before. The red line separates the routing domain and the switching domain at the leaf level. The traffic in the routing domain is load balanced. the TOR, or top of rack switch, get their VID automatically from the network ID of the switching domain. So that way, there's no need to configure anything. The spine switches receive a VID advertisement from the TORs and send out a request for a VID for each TOR they get an advertisement from. The VIDs are stored on the spine switches along with the port of acquisition. For routing information, the TORs store a CVID, or child VID, based on the VID that the spine acquired from that TOR. Here's the same topology again with the VID and CVID tables listed by the switches. In the VID tables for the spine switches, you'll notice that the acquired port number is appended to each VID. The TOR switches act as the root of the topology. As mentioned on the last slide, the TOR VIDs are derived from the network bytes of the switch domain, and the server IP addresses are in the same subnet as the TOR switch to keep the servers organized. Okay. Here's an example of how IP packet forwarding works from server to server with MTP. The message in this example is a packet going from a server rack in 120 to a server in rack 140. The packet is encapsulated inside of an MTP header with a source VID of 120 and a destination VID of 140. To determine which spine switch to send to, the TOR looks at the CVID table and determines to send it out port 1. The spine switch receives a packet and looks at the MTP header to the destination VID. It looks at its VID table and sends it out port 3 to rack 140, where the packet is sent to the correct server. MTP uses multiple messages in the control plane. Hello messages with a response, which are used for calibrating the hello interval, join requests and join responses, which are used for VID assignment, and leave messages that are used to remove a link or a switch. In the data plane, MTP packets contain an encapsulated IP packet. Every message using MTP is carried in a layer 2 frame. This is the format of the frame with MTP. It has the destination MAC, source MAC, and type fields, and then the new MTP code field with an MTP content field that depends on what MTP code was provided. MTP messages are processed by receiving TOR and spine devices. As stated before, code 9 denotes that the MTP packets carries an IP packet, which will then use the MTP forwarding process that was described before. Here are the MTP message types in more detail. Hello with no response is code 1 and is periodically sent out all interfaces to let other devices know that the device is still active. Hello messages with response is code 2. This is the hello message that is used to calibrate the round trip time to calculate the hello interval. The message is sent out all interfaces on startup. Join request messages are code 3. They're used by spine switches to request a VID and are carried in a frame that has the broadcast address as the destination and source address as the sending interface. Join response messages are code 4 and are used to inform the device that it offered VID that it now has a VID from that device. Leave messages are code 5 and are used to disassociate VIDs acquired or offered on that port. Prune messages are code 6. These messages have the receiving MTP device prune VIDs from their table in case of a failure. And for the data plane, the MTP packet is encapsulated inside of a layer 2 frame with MTP code 9. This is just used for sending data after the VID and CVID tables are built. MTP has different reactions depending on what type of failure took place. If a link failed, the switch that detected the failed interface will start VID pruning. Since this was detected by the switch, there's no need to wait for 3 missed hello messages. If a device failed, error recovery will take place after 1 hello message is missed for a faster failure detection. Devices will look at their VID table and determine which VIDs they received on the failed interface or link. They will then record the identified VIDs in a prune table and send an MTP prune message with the failed VIDs. Looking at the topology again, we can see what happens when VID 120.1 fails. which you can see denoted by the red and blue star in the link between T1 and S1. S1 detects a failure and stores VID 120.1 in a prune table and sends a prune message out every port except the failed port. The Tor devices will then inform the spine switches of the change. Now traffic sent to VID 120 will not send on port 1. Here's an example of the same interface failure with some slide animations. VID 120.1 is lost. S1 informs the other TORs, not including T1, that traffic to 120 cannot be sent using S1. The spine switches then inform T1 about the change. This process will take a minimum of 3 messages. Here's a visual that shows where MTP operates when routing traffic. As you can see, MTP cuts out the need to route traffic using IP addresses when sending from one server rack to another in the same folded clause topology. This helps cut down on complexity. In our MTP implementation, the Ethernet type field is set to a value not currently being used. Received frames with this type will be forwarded to MTP running in the Tor and spine devices. MTP does not impact any operation at layer 3, since traffic is routed based on the MTP header, which is processed before the IP packet. This also gets rid of the need for a routing protocol. MTP also does not impact any basic layer 2 operation. MTP will use link aggregation bundles between pairs of devices with the same IP. This allows you to disable lag in VLANs. It will also use tenant IDs on the interfaces, therefore isolating north-south and east-west traffic flow. So, how many operations can we overload with MTP? DCNs tend to use many different protocols together like VLANs, ECMP, BGP, and MPLS. Due to the intricacy of these protocols, it can introduce challenges like interworking complexity, high power consumption, fault isolation, troubleshooting, a fragile system, and high latency. With MTP, we are taking the functionality needed for DCNs out of these protocols and isolating them into one, therefore mitigating these errors. So now I'll talk a bit about work we're planning on doing in the future regarding MTP for DCNs. We will eventually expand the scope of the protocol to use a topology like this. This topology includes multiple pods in the same location. Before we were working with just one pod, but this expands the topology to have another layer of switches on top of the spine. This will introduce another layer of ports appended to the VIDs at the top level of the hierarchy as shown in the VID tables at the top here. We'll also work on a topology that routes traffic to and from a private network outside of the pod. This north-south communication is handled by the spine switches. If the traffic is traveling south to north, the spine switch will de-encapsulate the MTP header received from the Tor switch and send over the internet. If the traffic is traveling north to south, the spine switch will identify the destination network byte and find the corresponding Tor subnet to route it to. Before it sends a packet to the Tor, it will encapsulate the packet with an MTP header. Okay, so this concludes the presentation. If you have any questions, please feel free to leave a comment. And if you still have questions after the symposium is over, please feel free to reach out to me via email.